Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be going through week 11 material from Online Math 136 at Ivy Tech. We're going to start with section 6.1, which is all about composite functions, and we're also going to touch on topics from section 6.2 and 6.3. The first objective in section 6.1 is actually to be able to just form a composite function and understand what they are. So let's suppose for a minute that an oil tanker is leaking oil, and we want to be able to determine the area of the circular oil patch around the ship. So it's determined that the oil is leaking from the tanker in such a way that the radius of the circular oil patch around the ship is increasing at a rate of 3 feet every minute. So we know that the rate is 3 feet times time. And we know that the area of the circle is going to be pi times r squared. So in general, we can find the area of the oil patch as a function of time, t, by evaluating a of rt, and obtaining a of rt, which is the same as a of 3t, because we know it's spreading at a rate of 3 feet per minute. So if we plug 3t in to our equation for r, we get 9 pi t squared. So the function a of rt is a special type of function called a composite function because we're using two functions where one is kind of inside of the other function. So given two functions f and g, the composite function, denoted f composed with g, it's like f with this little circle in between them, like an open dot, is defined by f of g of x. Now the domain of f composed with g is the set of all numbers x in the domain of g such that g of x is in the domain of f. So this will be a little bit easier once we see some examples, but let's go through a few things first. So let's suppose that we have f of x is equal to 2x squared plus 3, and we have g of x equals 4x cubed plus 1. The first thing we want to find is f composed with g of 1. So in order to do this, what we do is we take f of g of 1. So if you think about the inside function here, we have g of 1. Now, if I were to ask you to find g of 1, I think everyone would know how to do that. All you do is you take 1 and you plug it into your g of x. So g of 1 is just going to be 4 times 1 cubed plus 1. So all we did is we just plugged in our 1 in for our x. And if we actually evaluate that, we need to follow order of operations, and we should get 5. So now what we have is we have f of 5, okay, because g of 1 is just a number, it's just 5. So now that we have f of 5, I know that you all also know how to do that. So all you do is you take 5 and you plug that in for x into your f function. So you have 2 times 5 squared plus 3. Now we know 5 squared is 25. 25 times 2 is 50, plus 3 is going to give you 53. Now, if we want g of f of 1, so this is kind of opposite, what we do is we always evaluate that inside function first. So in this case, we're trying to find f of 1. So we take 1 and we put it in to our equation for x, for f of x. So we have 2 times 1 squared plus 3. If we evaluate that, we get 5. So now what we're trying to find is g of 5. So we take 5 and we plug it in for x in our g of x function. So we have 4 times 5 cubed plus 1, and we get 501 for that one. Now you can also compose functions with themselves. So here we have f of negative 2. So what we do is we evaluate our inside first. So we take our negative 2 and we plug that in for x into our f of x function. So we have 2 times negative 2 squared plus 3. So again, we're just plugging it in for x right here. And if you evaluate that, you get 11. So really what we have is we have f of 11. And if you want to find f of 11, all you do is you just take 11 and you plug that in for x. So we have 2 times 11 squared plus 3. And again, if we follow order of operations and evaluate that, we get 245. Now, if we want to find g of negative 1, what that tells us to do is go ahead and find g of negative 1 first. So you find your inside function first. So if we take negative 1 and we plug it in, we get 4 times negative 1 cubed plus 1. You should get negative 3 for that. And then what we do is we find g of negative 3, which was our answer from the previous part. So g of negative 3, we're going to take 4 times negative 3 cubed plus 1. And again, if we follow order of operations, we should get negative 107 for that one. The next composite function. So let's say that we have a function f of x, which is equal to 2x squared minus x plus 4, and we have a function g of x, which is equal to 4x plus 1. We want to find f composed with g and g composed with f, and then we also want to find those domains. So if we want to find f of g of x, what we do is we take our g of x, which in our case is 4x plus 1, and we plug it in everywhere that we see an x in our original equation, our f of x. So we know, like I said, g of x is 4x plus 1. So really what we're finding is f of 4x plus 1. Now, if you remember from function notation, all you ever do with whatever's inside the parentheses is you plug that in for x. So we take 4x plus 1 and we plug it in. So we have 2 times 4x plus 1 squared minus 4x plus 1 plus 4. And then we follow order of operations. We can expand some of this stuff, combine like terms. So first, if we square our 4x plus 1, we're going to have 16x squared plus 8x plus 1. And then we also distributed through this negative, or negative 1. So you're left with negative 4x minus 1. And then we distribute our 2 out front that we had, and we get 32x squared plus 16x plus 2. And then we still have this minus 4x. And then we combined these like terms. The negative 1 and the positive 4 can be combined, and then it would be a positive 3. And then again, we combine some like terms. We have a 16x and a negative 4x, and we have a positive 2 and a positive 3. So if we combine everything that we have 32x squared plus 12x plus 5. So that's f of g of x. Now we know that the domain of g is all real numbers, as is the domain of the composite function. So the domain of f composed with g is just the set of all real numbers. All right, let's do it the other way around now. Let's say we have g composed with f. So we take f of x, which is 2x squared minus x plus 4, and we plug it in. So we have g of 2x squared minus x plus 4. So what we do is we take our 2x squared minus x plus 4, and we plug it in for x into g. So we have 4 times this whole thing. So we have 4 times 2x squared minus x plus 4. And then we still have this plus 1 kind of hanging out here. And we go ahead and distribute. So we get 8x squared minus 4x plus 16 plus 1. And then just like normal, we just combine any like terms that we have, which would be our 16 and our 1. So we're left with 8x squared minus 4x plus 17. The domain of f is going to be all real numbers, and so is the domain of your composite function. So the domain of g composed with f is still just going to be the set of all real numbers. So it's easy when they're both kind of nice things where you don't have any denominators, we don't have any square roots. It's just nice polynomials. Now here we have some fractions. So we have f of x equals 3 over x minus 5, and g of x equals 2 over x plus 1. And we want to find f of g of x and the domain. So first we need to find the domain of g, which if you look at it, the only thing where you're going to have an issue is at negative 1, because if you take negative 1 and you plug it in for x, you get negative 1 plus 1 in your denominator, which is 0. We can never divide by 0, so we need to exclude negative 1 from our domain. So we also need to exclude it from the domain of f composed with g. Now the domain of f is going to be x not equal to 5, because if we take 5 and we plug it in for x, we have 5 minus 5, we just get 0. Again, we can't divide by 0. So if we put g of x into this function for x, we know that g of x cannot equal 5. So if we go ahead and do that, what we want to do is we want to set g of x equal to 5 and find the value that makes that happen. So we have 2 over x minus 1, that's our g of x, equal to 5. And then you can just think of that as cross-multiplying or getting rid of your denominator by multiplying by x plus 1. So you have 2 equals 5 times x plus 1, and you go ahead and distribute. So you have 2 equals 5x plus 5. And if you go ahead and solve this by subtracting 5 and dividing by 5, you get x equals negative 3/5. So the domain of f composed with g of x is going to be x such that x is not equal to negative 1, because that caused an issue with your original function, your g of x, and also x not equal to negative 3/5. Okay, so again, we have the same two functions here. We want to go ahead and find f of g of x. So I think this is a slightly easier way to find the domain shown on this slide. So let's go ahead and find f of g. We take g of x, which is 2 over x plus 1, and we plug that in for x into our function f. So we have 3 over 2 over x plus 1, which looks a little nasty, minus 5. And then we need to do some simplifying here. So in order to get rid of this second denominator, this x plus 1, we multiply everything by x plus 1. So we have 3 times x plus 1. The 2 is just left by itself because the x plus 1s are going to cancel. And then we have minus 5 times x plus 1. We go ahead and distribute everything, combine like terms. So we have 3x plus 3 over 2. We distribute our negative 5, so we have negative 5x minus 5. We go ahead and combine our 2 and our negative 5, so we have 3x plus 3 over negative 5x minus 3. And if we want to write this a little more nicely, we can factor out a negative 1. So we still have 3x plus 3, and then we have 5x plus 3 in the denominator with the negative sign out front. And if you think about this for a minute, we still know that we have that original excluded value for our domain of g, which was negative 1. But if you look down here, if we set our new function, our f of g of x, if we set our denominator equal to 0, we have 5x plus 3 equals 0, we would get x is not equal to negative 3/5, which is the same solution that we got before. So either way is completely fine to find the domain, but typically you want to actually find the function as well, so it's a little easier to evaluate it all the way through first and then go back and figure out your domain. Okay, let's find f of f. So we know f of x is 3 over x minus 5, so if we want to find f of x, we take 3 over x minus 5 and we plug it in for x. So we have 3 over x minus 5, and then we have to do kind of the same trick because we have two denominators. So if we multiply everything by x minus 5, we're going to go ahead and get rid of it. So we have 3 times x minus 5. The x minus 5s attached to this piece just cancel, and we're left with minus 5 times x minus 5. And then we distribute, so we have 3x minus 15 left in our numerator, and then we have 3 minus 5x plus 25 when we go ahead and factor through our negative 5. Then we combine like terms, so we have 3x minus 15 over negative 5x plus 28. And then it's fine to leave it like that, or you could pull a negative sign out. So we know that the domain, we need to exclude 5 because that was from our original function that made our denominator 0. We also are going to have to exclude 28 over 5 because if we take 28 over 5 and we plug it in for x, it makes our new function equal to 0 as well. Okay, if we want to show that two composite functions are equal, what we have to do is we have to find f composed with g of x and g composed with f of x, and we need to show that they are both x when we evaluate them. Now this is going to be useful in a little while, so it's important that you understand this, but basically what we do is in order to find f of g of x, we just take whatever our function is, our g of x, and we plug it in for x into our other function. So we have g of x equals negative 1/2 times the quantity x minus 1. So if we plug that in for x, we have negative 2 times that whole nasty thing that I just said, the negative 1/2 times x minus 1, and then we have plus 1. And what you'll see here is the negative 2 times the negative 1/2, if we go ahead and distribute that through, it's just going to be a positive 1. So really we're just left with x minus 1 plus 1, which if you subtract 1 and add 1, those are going to cancel, so you're just left with x, which is what we wanted. Now we also have to check it the other way around. So we need to take our function f of x, our negative 2x plus 1, and we need to plug it in everywhere we see an x for g. So for this one, for example, we have negative 1/2 times negative 2x plus 1 minus 1. Go ahead and combine like terms, so the negative 1 and the positive 1, those cancel. So we have negative 1/2 times negative 2x. The negatives are going to cancel, and we're just left with x again. Okay, now we want to find functions f and g such that f composed with g is equal to h, if h of x is going to be 3 over x minus 5 squared. So what we want to do is we want to name two different functions where when we compose one with the other, this is our result. So if you look at kind of this inside function that we have here, we have x minus 5. We're going to call that our g of x. And then if you look at kind of what's left over, we have 3 over x squared, and that's what we're going to call our f of x. So if we go ahead and check this, if we take g of x, which is x minus 5, and we plug it in everywhere we see an x in f of x, we're left with f of g of x is equal to 3 over x minus 5 squared, which is exactly what we wanted. So this is kind of a working backwards approach. Okay, section 6.2, this is where we're going to be using some of the stuff that we just learned about composite functions. In particular, we're finding one-to-one and inverse functions. So if we want to determine whether a function is one-to-one, we kind of have to look at this a little bit. And basically, it's exactly what it sounds like. For every one x, we have to have one y and the other way around. So if any two different inputs in the domain correspond to two different outputs in the range, then your function is going to be one-to-one. So if you look at this first one, for example, all the way on the left here, we have 3 values for x, they're mapped to 3 different values for y. So we don't have any x's repeating, we don't have any y's repeating, so that one's going to be a one-to-one function. But if we look here, we have all different x's, which is good, but we actually are mapped to the same y 2 different times. So this one is not a one-to-one function. It is a function, but it's not a one-to-one function. And this one over here, we have a different issue. We have one x value that's actually mapped to 2 different y values. And that one's not a function at all because x1 has 2 images, both y1 and y2. And if you recall, this can never be the case. So this one is not even a function, let alone a one-to-one function. Okay, so let's look at this one here. For the following function, the domain represents the age of 5 males and the range represents their HDL, which is their good cholesterol, given in milligrams per deciliter. So we have these different ages and we have their HDL cholesterol and we want to decide if it's one-to-one. And if we look at this, it's actually not because we have 2 different inputs, which are ages 55 and 61, which actually map to the same HDL cholesterol. So that one's not going to be one-to-one. Now, if we look down here, we have kind of a different data set given. We have some coordinates. We have -2, 6, -1, 3, 0, 2, 1, 5, and 2, 8. Now, for this one, it actually does appear to be one-to-one. There are no 2 distinct inputs that correspond to the same output, so we don't have any repeating x's or y's. Now, if you recall, the vertical line test allowed us to see if something was a function. The horizontal line test works in the exact same way, but basically it just lets you know if it's a one-to-one function or not. So if you think about it, we have a little graph down here. The actual graph of whatever equation we're talking about, our f of x, that's our blue, okay? And then what we've done is we've drawn this pink horizontal line. And what you can see is that our f of x1 on our graph is the same as f of x2, okay? And we've called them both h. But x1 is not the same as x2, so that means that f is not a one-to-one function. So if you recall what the graph of y equals x squared looks like, you'll remember it's a parabola. If you think about a parabola, as we start to draw our horizontal line and move it up and down, we do see that it crosses our graph in more than one place. So that means that it's not going to be one-to-one. But if you think for a minute about our x cubed, this is the one that kind of looks like a sideways stretched out S. Any horizontal line that we draw, which they're all shown kind of in pink here, if we draw any horizontal line, we're only going to hit our graph in one place. So that means that our function g of x equals x cubed is actually a one-to-one function. Another nice theorem to know is that if a function is increasing on an interval I, then it's one-to-one on that interval. And if it's decreasing on an interval of I, then it's also one-to-one on that function of that interval. So when you go from increasing to decreasing or decreasing to increasing, that's where your function no longer becomes one-to-one. But if you're talking about a strictly increasing or strictly decreasing function, then you do have something that is in fact one-to-one. Okay. Now we want to go ahead and determine the inverse of a function defined by a map or a set of ordered pairs. So these are pretty easy. Let's suppose for a minute that we have a function f, which is one-to-one. Then to each x in the domain of f, there's exactly one y in the range, since f is a function. And to each y in the range of f, there's exactly one x in the domain, and that's because our function is 1 to 1. Now the correspondence from the range back to the domain is called the inverse function. So if we look at an example here, we have states and we have populations. We have Indiana with 6.2 million people, Washington with 6.1, South Dakota with a little less than a million, 0.8 million, North Carolina with 8.3 million, and Tennessee with 5.8 million. So we see we have 5 different states, 5 different populations. So we have 5 different x's, 5 different y's. So this is definitely a function, definitely a one-to-one function. The domain is going to just be all of our x's, that's our states, and the population would be our y's. But if we want to find the inverse function, all we need to do is just flip those two things around. So in this case, our new domain for our inverse function would be all the values of the population, and the new values for our y, or our range, would be all of the states. So the domain of the inverse function, that's the one that we have on the right here, is going to be 0.8, 5.8, 6.1, 6.2, and 8.3. Those are all of our populations. And then the range is going to be all those values for states: Indiana, Washington, South Dakota, North Carolina, and Tennessee. Okay, if we're given an order pair, we can do the same thing. Now, they already tell us it's 1 to 1, but I would always suggest just verifying that. So if you look, we don't have any repeating x's, we don't have any repeating y's, so we're good. We have a 1 to 1 function. Now, if we want to find the inverse, it's really, really easy. All you have to do is just flip your x's and your y's around. So instead of -5, 1, we now have 1, -5. So we've just interchanged the x and y's. Now 3, 3, when we interchange those, it doesn't change at all actually, so you're still just left with 3, 3, same thing with 0, 0. If we take 2, -4 and we flip it around, we get -4, 2. And if we take 7, -8 and flip it around, we get -8, 7. So the domain of our function is going to be basically just all of our x's, and this is from our original function. We have -5, 0, 2, 3, and 7. So this is from our original. Now if we look at the range of our function, we had a -8, a -4, a 0, a 1, and a 3. If you look at that though, the range of our original function is actually the same as our domain of our new inverse function. And then the range of the inverse function is actually going to be the same as the domain of the original. So domain and range just flip-flop when you're talking about inverse functions. And if you look here, here's kind of a graphical depiction of this. So we have domain of f, range of f. We have some function f that takes us from our domain to our range. And then we actually have our inverse function f inverse, which is written as f with like a little -1 as kind of a superscript up top. And that actually takes us from our range back to our domain. So they kind of undo one another. Okay, so here's another representation. Here we have an input x from our domain of f. If we apply our function f, we have f of x. And then if we apply our inverse, it kind of, like I said, it undoes it. So we're just left with x. And then again, if we take our input x now from our inverse function, we apply f inverse. So now we have f inverse of x. If we go and we apply f to that, so we take f of f inverse of x, we are again just left with x. So we have these two rules here. So if we have f inverse of f of x, that should be equal to x, where x is in the domain of f. And if we have f of f inverse of x, that should be equal to x, where again x is in the domain of, this time, f inverse. So before we're actually tasked with finding our own inverse functions, the first thing we want to do is actually verify them. So they give us some things and they want us to actually show that, yep, these two things are inverses of one another. So let's say we have g of x equals x cubed, and g inverse of x is equal to the cube root of x. So those seem pretty close to one another. It seems like cube root and cube would in fact undo one another. But they do not, or sorry, that they do actually, sorry. So in order to verify this, what you actually have to do is you need to take your g inverse of x, which is cube root of x, and you need to plug that in to your x cubed function. And then you also have to do it the other way around. So you have to take your x cubed function, plug it in for x into your g inverse of x. So right here, if we take cube root of x cubed, You should recall that cube root and cube are going to cancel one another out, just kind of like we suspected, and so we're just left with x for that one. And if we take cube root of x and then raise that to the third power, we again get x, okay? And this is for all x in the domain of G and for all x in the domain of G inverse. So since those two both resulted in x's, we do have two functions that are inverses of one another. Now here we have f of x equals 2x plus 3 and f inverse of x equals 1/2 times x minus 3. This one isn't as clear right off the bat whether or not these are inverses of one another, so again we just need to verify. So for this first one, what we do is we take our 2x plus 3 and we plug it in for x into our f inverse. So we have 1/2, that's from here, right here, and then we have times 2x plus 3, that's our new x, and then we have minus 3. And if you combine like terms, we have plus 3 minus 3. You're just left with 1/2 times 2x, which is just going to be x. Now we do it the other way around. So we take our 1/2 times x minus 3 and we plug it in everywhere we see an x in our original function, our f of x. So we have 2 times 1/2 times x minus 3 plus 3. So we're left with x minus 3 plus 3, which is just going to be x. Okay, let's do another one. Let's say we want to verify the inverse of f of x equals 3 over x plus 5, and we want to verify that its inverse is going to be 3 over x minus 5. So we want to note that the domain of f is going to be all numbers x such that x is not equal to -5, and the domain of g is going to be all numbers x such that x is not equal to 0. So if we go ahead and take our f of x and we plug it in to our f inverse, we have 3 over x minus 5, so two fractions minus 5. And if we go ahead and multiply by x plus 5 over x plus 5, we're going to be left with 3 times x plus 5 over 3 minus 5, which is going to be x, provided that x is not equal to -5, because we know if x is equal to -5, that causes us to have a 0 in our denominator, which is never any good. And then we also need to do it the other way around. So we need to take our 3 over x minus 5, and we need to plug it in for x here. So we have 3 over x minus 5 plus 5. And if you go ahead and combine like terms, minus 5 plus 5, those are going to go away. So we really have 3 over x. And if you think about that for a minute, we can multiply by the reciprocal, and you're just left with x, provided that x is not equal to 0, because again, if you plug 0 in for x, you do get a 0 in a denominator, which is no good. All right, next thing we want to do is actually obtain the graph of the inverse function. So if we're given some point AB, and we want to find kind of its inverse, if you recall, what we would do is we'd flip our x's and our y's around, so we'd be left with BA, which is kind of this pink point that's shown here. The other thing that you'll see is we have this line y equals x. That's just a 45-degree line, basically, that just goes right through our origin, creates a 45-degree angle with our x and y axis. And if you think about it, if you take this blue point, this AB, and you kind of flip it across this line, you're left with BA. So this is kind of a nice way to find the inverse of your graph without having to flip every single individual point. There is a nice theorem that goes with this. Basically, the graph of a function of f and the graph of its inverse, f inverse, are symmetric with respect to the line y equals x, which is the line that we just talked about. So if you look here, we have this blue line, f of x, and again, we have this line y equals x just kind of drawn here for a visual aid. And then if you take this blue line and you can kind of imagine folding it over this diagonal line, you actually end up with this pink line right here, which is its inverse. And you'll notice anytime that it actually hits this line y equals x, its inverse always goes through that line as well. So if we have something like this, and we want to draw its inverse, one thing you can do is just draw your line of y equals x right on there and go ahead and flip it across. If that's hard for you to see though, one thing that you can do is just flip every individual x and y. So 2, 1 now becomes 1, 2, so we now have a point up here. -1, 0 becomes 0, -1, which is this point down here. And -2, -1 becomes -1, -2, which is this point down here. And then if we just connect them all kind of in the same fashion, you'll end up with this pink line here, which is your inverse function. Okay, now that we've learned how to verify if something is the inverse of something else, we want to actually be able to find it. So there are several steps that we do in order to find an inverse. So let's say we have f of x equals 2x plus 3. We want to graph f and the inverse on the same coordinate axes. So in order to do this, in order to find our inverse, what we have to do is, first thing, my suggestion is just ignore this f of x and just think of it as y, because that's really all that it is. And then what you do is everywhere you see a y in your equation, you put an x. Everywhere you see an x in your equation, you put a y. So basically you flip-flop your x's and your y's, and then you just need to solve for y. So in our case, we would have y equals 2x plus 3, and then we'd flip our x's and our y's around, so we'd be left with x equals 2y plus 3. Step 2 is to go ahead and solve the implicit equation for y in terms of x. So what we want to do is we just want to isolate our y. Okay, so we want to get y by itself. So in order to do that, we would subtract 3 from both sides. And we rewrote it so that we have our 2y on the left-hand side, which is a little nicer. So we have 2y equals x minus 3. And then divide everything by 2. So you're just left with y equals 1/2 times x minus 3. Or x minus 3 over 2, that would be the same thing. So that is your inverse function. And then you can go ahead and check the result by showing that f inverse of f of x is equal to x, and f of f inverse is also equal to x. Those are the same steps that we took before. And if you do that, you will get the same thing. Now, if you think about the graph, we had our original function 2x plus 3. That's just a line that goes through 0, 3, which is our y-intercept, and has a slope of 2. So you go up 2 and over 1 to create that blue line. And then over here, we actually also have just a line that's going to have a slope of 1/2. And if we were to distribute this, it would have a y-intercept of -3/2, which is just -1.5. And if we go ahead and draw that pink line, it looks something like that. So if you take the blue line and you reflect it across this line, y equals x, you do end up with this pink line down here. So again, here are our steps. Step 1 is just in y equals f of x, interchange the variables x and y to obtain x equals f of y. This equation defines the inverse function f inverse implicitly. And then, if possible, solve the implicit equation for y in terms of x to obtain the explicit form of f inverse. So you're going to end up with something like y equals f inverse of x. And then you can go ahead and check the results. So let's do another one. Let's say we have f of x equals 2x plus 1 over x minus 1. We know that x cannot equal 1 because if we plug 1 in for x, we have an issue. We get a 0 in our denominator. This is going to be 1 to 1, and we want to go ahead and find its inverse. So in order to do that, the first thing that we do is, instead of writing it with f of x, we just write it with a y. So we have y equals 2x plus 1 over x minus 1. And then we interchange our variables x and y. So we replace y with x with y. So we get x equals 2y plus 1 over y minus 1. And then we would like to solve for y. Now, anytime you have this where you have y in a numerator and a denominator, the best thing to do first is just go ahead and get rid of your denominator. So in order to do that, you want to multiply both sides by y minus 1. So you have x times y minus 1 equals 2y plus 1. So we no longer have a fraction, which is nice. And then you go ahead and distribute your x through. So you have xy minus x equals 2y plus 1. And then what you want to do is you want to get everything that has a y attached to it on one side and everything else on the other side. So in this case, we move the 2y to the left-hand side, so it's with this xy, and we move this negative x to the other side, so it becomes a plus x. So we've taken everything that's attached to y and we moved it to the left-hand side, and everything else we've put on the right-hand side. And then what we can do once we have that is just factor out a y. So we can take a y out of everything. So we have y times x minus 2 equals x plus 1. And then we can just divide by x minus 2. So we get y equals x plus 1 over x minus 2. And really we should write that as f inverse of x. It's going to be x plus 1 over x minus 2. X is not going to equal 2. And we could also check this result just by plugging it back in. This is pretty nasty. There's nothing wrong with doing this. It's certainly a good idea, but you end up with a lot of fractions, and I think it's actually a little easier to screw up than the problem itself. Okay, let's find another inverse. Let's say we have y equals f of x is equal to x squared if x is greater than or equal to 0. So if you recall, y equals x squared was not a one-to-one function, but if we just look at the part where x is greater than or equal to 0, then it is indeed a one-to-one function. It's just the increasing part of the function. So again, we just interchange our variables x and y, so we get x equals y squared. And then if we want to solve for y, we take square root of both sides. So we get y equals square root of x. Now, typically, if you recall, when we take square root, normally we put a plus or minus out front. But given this domain restriction, what we've done is we've kind of limited ourselves to positive x's, which means that we're limiting ourselves to positive square root as well. So what we end up with is y equals the positive square root of x. So that is actually our inverse function. And then we could check this by taking our f of x, which is x squared, and plugging it into our equation. So we have square root of x squared. We know that's going to be absolute value of x, which is just x. And then we can also do it the other way around. We can take square root of x and plug it in. Square root of x squared is just going to, again, be x. And if you think about the function, this blue line here, this is half of your x squared function. It's just the values where x is greater than or equal to 0. And then if you recall what your square root function looks like, it's this pink line here. And those are actually inverses of one another. So here's a very nice summary. This can be found in your textbook as well. But if a function f is 1 to 1, then it has an inverse, which we denote with f -1 or f inverse. The domain of f is going to be the same as the range for your inverse, and the range of f is going to be the same as the domain of the inverse. So ranges and domain flip-flop. If we want to verify that f inverse is the inverse of f, what we need to show is we need to take our f of x, plug it into our f inverse, and we need to make sure that that is x. And we also need to take our inverse function, plug it into f, and make sure that that is x as well. The graphs of f and f inverse are also symmetric with respect to the line y equals x. Okay, now we're going to talk about section 6.3, which is exponential functions. So first thing we want to do is just evaluate these. Now this is something that you may not have done before, so I just want to make sure everybody is comfortable with it. Most calculators have either an x to the y key or a caret key that allows you to work with exponents that are not x squared or x cubed. So you probably already know how to do x squared and x cubed on your calculator. But if you're just using a specific square and cube button for that, then you may not have come across this before. So for a, for example, what we want to do is 2 to the 1/4 power. So if you have the calculator that has the caret, you're going to do 2 caret 1.4 and then hit enter. If you have the calculator that has the x to the y key, you're either going to hit 2 and then the x to the y and then the 1.4, or some people may have what I like to call a backwards calculator where everything's kind of reversed. In some cases, you may need to put your exponent in first. So just make sure that you're getting these answers that we have here, like 2.64, and the other ones are written here as well. So you could try 2 to the 1.41 power, 2 to the 1.414 power, 2 to the square root of 2 power. You'll see that they're all close, okay, because square root of 2 is an irrational number that is about 2.41. Okay, we have some laws of exponents here, which I know we've touched on in the past in some of the review sections, but I kind of want to remind you guys to make sure everybody remembers this stuff. So ST, A, and B are all going to be real numbers. A is greater than 0 and B is greater than 0. So if you recall, if you're multiplying two things, you have the same base. In order to solve that, basically you can write it with just one base and you can add the exponents. So if you're multiplying, that can change into addition. But if you have something where you have some power to a power, then you actually multiply those two powers. That's given right here. If you have two things that are multiplied within parentheses and then that is all raised to a power, you can actually split it apart. So you can raise a to the s power and b to the s power and then multiply. If you recall, 1 to any power is just going to be 1. And then if you remember anything about negative exponents, hopefully what you remember is that you can always take it and move it into the denominator and make it positive. So if you have a to the negative s power, that's the same as 1 over a to the positive s power. And in addition to that, you could take an s out because of these two rules that we've already learned. So you could write this as 1 over a to the s power. And then the other thing is that anything to the 0 power is just going to be 1. Okay, so let's say we have a function f that has the following two properties. The value of f doubles with every 1 unit increase in the independent variable, and the value of f at x equals 0 is 5. So we know that f of 0 is 5. And what we have here is we have kind of this table here that's given 0, 1, 2, 3, 4, and then we have these values where you have f of x is 5, 10, 20, 40, 80. So you can see this pretty clear pattern where we're multiplying by 2 each time. So this is a great example of an exponential growth function because what we have is we have some value of 5, that's kind of our initial value, and then every time we have an exponent, we multiply by 2 to that power, okay? So in order to write our equation, we can kind of do this iterative process until we get there, and what you should see is that we have 5 times 2 to the x power. That would give us the function that we're seeing right here, which is an exponential growth function. So exponential functions are always going to be in the form of f of x equals c times a to the x, where a is going to be a positive real number that's not equal to 1, and c is not going to equal 0, it's going to be a real number. The domain of f is the set of all real numbers. The base a is called our growth factor, and because f of 0 is going to be c times a to the 0, which would just be c, we call c the initial value. So it's kind of our starting point. So we have this nice theorem here for an exponential function, f of x equals c times a to the x, where a is greater than 0 and not equal to 1. If x is any real number, then f of x plus 1 over f of x is going to be equal to a, or we can say that f of x plus 1 equals a times f of x. So the first thing we want to figure out how to do is identify a linear versus an exponential function. So in order to do this, let's look at this first example. The first thing we do is we just find average rate of change, which hopefully you remember is just a fancy name for slope. So what we do is we take y2 minus y1 over x2 minus x1. This should be really easy for you guys at this point. So you take 2 minus 5 over 0 minus negative 1, and we get negative 3. And then if we do the same thing for all of these pairs all the way down the line, negative 1 minus 2 over 1 minus 0, again we get negative 3. And you'll see all the way down we get negative 3. If when you're evaluating average rate of change, if you get the same value all the way down, that means that you actually have a linear function. Now we'll talk about, I'm going to ignore this ratio of consecutive outputs because for this one, if you notice that your average rate of change is the same all the way down, there's no need to calculate this right here. So since the average rate of change for every 1 unit increase in x is negative 3, it's going to be a linear function. That means that the slope is going to be your average rate of change, that's your negative 3. And the y-intercept, that's just the value when x is 0, so in this case it's 2. So if we wanted to write an equation, it would be y, or f of x, equals negative 3x, because that's our slope, and then plus 2. All right, let's look at another one. So this one, we have kind of different values here. We have different values for x and y. And if we start calculating average rate of change, we get 16 minus 32 over 0 minus negative 1. That gives us a negative 16. And then if we do it again for this next pair, we get 8 minus 16 over 1 minus 0. We get negative 8. And we can tell right away that these are not the same, okay? If you get something where the first two, or however many you do, if you get something where it's not the same, that means you have something that's not a linear function. If the average rates of change are not all the same, then you don't have a linear function. So this one, you want to go ahead and calculate this ratio of consecutive outputs, and that's actually really easy. Typically, we have consecutive inputs, so we have like values for x that are all separated by 1, like from negative 1 to 0, that's 1 space, from 0 to 1, that's 1 space. So all we have to do is just divide our y2 by our y1. So we take our 16 divided by 32, that's going to be 1/2. We take our 8 divided by our 16, again that's 1/2. 4 divided by 8, that's 1/2, and 2 divided by 4, that's also 1/2. And if you notice, these are all consistent, okay? So for this function, again, the average rate of change from negative 1 to 0 is negative 16, but from 0 to 1, it's negative 8. So since it's not constant, the function is not linear. But the ratio of consecutive outputs for a 1 unit increase in the inputs is a constant, it's 1/2. Since it's constant, the function is exponential. The growth factor is going to be this ratio that we just found here, which was 1/2. And then in order to get the initial value, we have to look where our x is 0. So if we look at x equals 0, we get y equals 16. So if we want to write our equation, we have our initial value, which is 16, multiplied by our growth factor, which is 1/2, raised to the x power. So we have g of x equals 16 times 1/2 to the x power. And we have another one here. Again, we have different values for x and y. If we calculate average rate of change, we get 2, 3, 4, 5. Those are not all the same. And then for this one, if we calculate ratio of consecutive outputs, we have 4 divided by 2. That gives us 2. Then we have 7 divided by 4, which does not give us 2. Okay, so this one doesn't have average rate of change that's all consistent, and it doesn't have ratio of consecutive outputs that's consistent either. So since those are not the same, it's actually not exponential or linear. All right, now if we want to graph exponential functions, the first thing we can learn how to do is just plug in points, okay? So you should already know how to put all of this into your calculator, but what we've done here is create a little xy chart. We have the function f of x equals 2 to the x, and then we plug in some values, and you'll see we have some values for y out. And if we graph this, it looks just like this right here. Okay, so it's a pretty nice little curved function. It goes through 0, 1, it's increasing. So this is kind of a list of properties that holds true for any exponential function that you have where you have f of x equals a to the x, where a is greater than 1. Okay, I want to make sure we distinguish this because a less than 1 actually looks a little bit different. So the domain is going to be all real numbers. The range is going to be all positive real numbers. There aren't any x-intercepts. We actually have an asymptote, but the y-intercept is 1. The x-axis, which is just the line y equals 0, is going to be a horizontal asymptote as x approaches negative infinity. F of x equals a to the x, where a is greater than 1, is going to be an increasing function. It's going to be 1 to 1. We could use our horizontal line test in order to see that. And then it always contains the points 0, 1, 1a, where a is our growth factor, and negative 1, 1 over a. It's going to be nice and smooth and continuous. It doesn't have any corners or gaps, kind of similar to our quadratic equations or our polynomials. Now if we have something like this where you have f of x equals 1/2 to the x, this does not fit with that same rule that we had for the other one because now we have a number that's actually smaller than 1. And if we graph this, you'll see that it's actually decreasing instead of increasing, but it looks very similar other than that. So what you might notice is that if we have 2 to the x, if we replace x with negative x, that means we have 2 to the negative x power. Now, if you recall what we have about negative exponents, we can move them to the denominator if we make them positive. So this is actually the same thing as 1/2 to the x power. So really what we've done is we've reflected our graph around our y-axis. So we have additional properties for functions where you have f of x equals a to the x, where we have some number between 0 and 1. Okay, so some number that's less than 1, larger than 0. The domain is going to be all real numbers again. The range is again positive real numbers. There aren't any x-intercepts. We have the same y-intercept, it's just 1. We have the same horizontal asymptote, just y equals 0, but this one is going to be a decreasing function, okay? It's still 1 to 1, but it's decreasing. And then we have some different points that it contains. It still contains 0.01, but it contains 1a and negative 1, 1 over a. And the graph is going to be, again, smooth and continuous, just like other polynomials, no corners or gaps. We can also use transformations in order to graph these. So now that we know what our base graph looks like, we can use some transformations. So we know that y equals 2 to the x looks something like this on the right, or sorry, on the left. Now we've replaced x with negative x, so we want to graph the function 2 to the negative x minus 3. So since x is replaced by negative x, we reflect around your y-axis, so instead of being increasing, it's now decreasing. And then with this minus 3, that actually moves it down 3. So we take this and we scoot it down 3, and so we end up with a function that looks just like this over here on the right. Next thing we want to do is define the number e. So the number e is just defined as 1 plus 1 over n to the nth power as n approaches infinity. So in calculus, this is expressed using a limit notation, E is going to be the limit as n approaches infinity of 1 plus 1 over n to the n. And it's approximately like 2.72, that's the value. So if we want to graph our function y equals e to the x, what we could do is we could plug in some points. Since e is 2.72, that's a number that's larger than 1, so we know that we're going to have something that looks like it's increasing, right? So it still goes through this point 0, 1, still has our same asymptote, but just some of these values are a little bit different. And again, we can use transformations. So if we want to graph the function y equals negative e to the x minus 3 power, we start with y equals e to the x, which we know looks like this on the left. We're going to multiply by a negative 1, and that's actually multiplying our y value. So we're going to reflect around our x-axis. So this one's actually flipped kind of upside down across our x. So we end up with something like this. And then if you recall that minus 3, that's actually kind of inside of our function. So that's going to move it either left or right. And if you recall, when we have a minus 3, that actually moves it to the right. So we shift to the right 3. So it looks something like this. We can also solve exponential equations. So if we have something where we have a to the u power is equal to a to the v power, then we know that the exponents have to be the same. So u has to equal v. So let's say we have something like this. Let's say we have 2 to the 3x minus 1 equals 32. So the whole goal of this is to get it so that we have the same exact base. So if we rewrite this, if you recall, 32 is actually just going to be 2 to the 5th power. So now we have 2 to the 3x minus 1 equals 2 to the 5th. Since we have the same base, we can essentially just ignore our bases. So really we have 3x minus 1 equals 5. Add 1 to both sides, divide by 3, and we get x equals 2. Now this one over here on the right, this is a little messier. We have e to the 2x minus 1 equals 1 over e to the 3x times e to the negative x to the 4th. So first thing we want to do is go ahead and use some of our rules that we've figured out. E to the negative x to the 4th is going to be e to the negative 4x. So we have e to the negative 4x over e to the 3x. And if you recall, when you divide things and you have the same base, you can subtract the exponents. So we have e to the negative 4x minus 3x, which is going to be negative 7x. So now we have e to the 2x minus 1 equals e to the negative 7x. Again, since we have the same bases, we can ignore them. So we're just left with 2x minus 1 equals negative 7x. And we would add 7x to both sides, or, well, actually, I'd probably subtract 2x from both sides and then divide by negative 9. So you get x equals 1/9. So we have some summaries here. These are the same things that we already went through, but if you have some function where you have f of x equals a to the x, where you have some number a greater than 1, you're going to have an increasing function. But if you have something where you have like a fraction that's between 0 and 1, then you're going to have something that's reflected around your y-axis. It's going to be decreasing. So that's it for today. If you guys have questions, go ahead and please let me know now. I think there's one person logged on. You can type your questions right in that question box. So if you have anything, please go ahead and type it there. All right, I don't see any questions. Feel free to email me. Oh, I have a question here where the recording lecture is found at. So you should get an email within the next day or so that asks you if you enjoyed the lecture and kind of any feedback that you wish to give. And my email address should be on there. I think it should also be on the confirmation email that you got about the lecture itself. So this is recorded, I record them, and then I send them, and then they're posted to YouTube. So I'd be more than happy to send you that link if you just email me. So again, my email address can be found on those registration links that you got. It's pseeburger, PSEEBURGER @ivtech.edu. So just shoot me an email if you want a link to the recorded lecture, and I would be happy to send it. All right, I think that's it for today then. Thanks for joining.